And another important is to maybe I can. So if I get questions over here, it will be on my laptop or on this. Okay, then I can. Possibly.
After break. It was good.
How was your break?
It was good. Went to Iowa.
Oh, nice, nice. Is it family?
Yep.
We
Went to,
Oh.
I don't know if you saw anyone knows about like soccer. The today.
Yes.
Something.
Did you play it in the field house like last time?
Yeah.
There are two. The left hand side is cut off and it's on the right side.
maybe we need to.
Thanks.
Interesting.
Maybe we need. Okay, but okay.
Yeah.
I think they're gonna try and do it again next week.
So is it connected to Zoom? Because smartphones can join.
Yeah, I think he's doing.
Okay, okay. Maybe we need to reset.
Let me try to see that what kind of connection you have. So normally, this is C, right?
Yeah, well, let me try, maybe, yes.
There should
I
be
have a bit of luck
somewhere.
with the PowerPoint, maybe?
No, I think it's problem with the monitor. It's not a file.
Yeah, okay, yeah.
Yeah,
right.
even if you before, even before you open the file.
So I go to displays. or-
Yeah.
Yes, mirror
And then I do mirror displays or something?
Yeah.
We can try, yes.
Where is that?
I think it's the drop down there here.
Arrangement, you have to probably click on arrangement.
Arrangements?
Probably.
No.
Yes, mirror display. Yes,
And then unclick
Is
the
this-
mirror display. I think.
yes.
It's.
Oh,
Yes,
Yeah.
now
But
It's
things still,
oh, yeah, it's still a problem.
Through the, yeah.
that's weird.
How about if you click scale?
maybe we need to change the resolution according to the
I
scale.
love this.
Huh?
Yeah.
I think you try scale. If you look scale.
This was like most of the semester.
Okay, I saw this the
Okay,
day.
the first one, 1080p.
I'm trying to.
Very good. You guys have been through this before, that. When they should have updated technology, I mean, there's no T connector here.
What they have in the original.
I might go in there.
That's great. That's beautiful. My grandparents. Solar. They went, it's near Cedar Rapids, I was in. Oh, nice. Yeah. Did you see the Wi-Fi retreat that's happening? No. I think we went to a cabin for a couple days and do a cabin. January. It's January. It's probably January 11th or 13th, which is the. Sorry, cancel your. Yes.
Среду все, что через 10 минут предприятия.
Maxim, you think it's good to go? Yeah. Okay. Is there some online thing you wanted to connect to? You have already done that. All right. Okay, very well. Okay, today we're very happy that we all know Maxim will give us a cosmology seminar, and he's going to talk about accelerated dark matter. Maxim, please.
Well, thank you so much. I decided to go with this topic because we had already some talks about novel attempts to detect light dark matter, and I'm going to tell you what is the best way, in my opinion. Okay. So I'm going to cover some topics that I worked on in the collaboration with people from Tsinghua University, Vienna, University of Victoria, also Oslo, and Marianne Moore is a student at Harvard. And this is a group from Triumph, and Harry is at Stanford. So we all know that a lot of the universe's energy density is in the form of the matter that is not variance, but has the ability to cluster, and we see evidence of this clustering at starting as early as CMB. We measure the overall energy density. The problem is the smallest sort of distance scales on which we infer the existence of dark matter is 10 to the 21 or so centimeters, and we need to, if we ever want to make a connection directly with an experiment, we need to go down to like 1 meter perhaps, and so to make an extrapolation by 20 orders of magnitude is not possible without any kind of theoretical ideas behind. So here is the first step, and there is a very good thought, but this is not written in stone, that the dark matter could be a new type of particles. What kind of works into this direction is that the cosmological model that we know and love, such as lambda CDM, has 6 parameters, and these 6 parameters describe everything we more or less know about the universe, and it's very simple. And so this simplicity is actually perhaps is a hint that the dark matter might also be a simple thing. In particular, it's been in place since the matter radiation equality, as we know that for sure, and perhaps it's in the form of the unknown particles, and that will allow to make a jump from this scale here to scale here, and invest into the experiments looking for dark matter directly in the underground laboratories under a very strict sort of radiation pure environments. My talk would be of making use of the already existing experiments to extract maximum information from them, and maybe cover some blind spots for that method. So here is an example of particle physics slide where we think what kind of particles dark matter could be. Dark matter can be very well be a massive particle that has large interaction rates with other particles, and therefore it can be, for example, produced at colliders and so on. In the early universe, we kind of think that the production goes the other way. Initially, we have as many dark matter particles as the rest of the species, but let's say they're stable, or metastable, very long there. But when the temperature in the universe drops below their mass, they try to, according to sort of a Boltzmannian preference, to self-deplete by annihilating to the Standard Model states. And this annihilation can occur through a Z boson, the Higgs boson, through maybe some additional fancy particles. Here is an example of the supersymmetry model where the two dark matter particles annihilate into quarks by exchanging the supersymmetric partner of the quarks. And some models are bound to have only very heavy dark matter, sort of in particular supersymmetry. Is no reason to expect that these particles would be, say, in the MeV range. They roughly be the scale of the supersymmetry, perhaps a little lower than the rest, but sort of in a good guess would be 100 GeV regime and heavier. Okay. However, this is not the only possibility. You can have dark matter coming together with its own force. Here, this pictured by a dark photon, whose mass is not necessarily very heavy, and then this whole process is can have a same size annihilation cross section while maintaining particles at a lower mass. In this way, you can create a realistic dark matter models with masses running as low as like a few n. Very well. So this is again particle physics kind of slide. So we think about all these fancy particles from the say supersymmetric sector as very heavy. Then we have a Standard Model extended by at low energy by a bunch of the sort of high dimensional operators. But if we have also light particles like dark photons and light dark matter, then we have to put them explicitly in. And in principle, there's been much work done in this direction, classifying all possible interactions from very general grounds that the dark matter can have with the regular particles. So here's two examples of models where the masses of dark matter particles can be as low as a few MeV without contradicting anything we know. And these are models based on dark photon mediation or dark scalar mediation, as already mentioned. And given that there's a lot of efforts of detecting a Standard Model, weakly interacting massive particles at the weak scale, it would be very strange not to explore possibilities around it. And now is the time to explore all possible models of dark matter. That's what I'm going to do. So one of the most successful experiments operating in various places in the world, that is in the US, in Italy, in the Sasko laboratory, and in China. The experiments based on dual phase xenon PTCs. So these are typically now multi-clone scale experiments that have liquid and gaseous xenon. The signal consists of two basically paths. If the dark matter interacts with the xenon atom and pushes it, the atom gets ionized. The ionization creates a scintillation light right away. That's called S1. And then the ionization drifts into an electric field and with a time delay it creates in the gaseous phase a cascade that leads to further scintillation, and it's called S2. So using these two things, the dark matter experiments can discriminate rather well between the electron recoil and the nuclear recoil. Here is the sensitivity of the xenon one-ton experiment. This is already a whole slide, and you can see that there is nothing seen, at least in this paper, by xenon one-ton. And basically you see the two paths to this curve. This scaling part here is just reflects the fact that when you have the dark matter heavier, you have fewer of these particles. So it's 1 over mx kind of where x is the dark matter mass decoupling of the signal. And over here you see a rapid deterioration of the sensitivity related to the fact that light dark matter does not leave much of a recoil in the detector, and you need, at the very least, you need 13 electron volts of energy available energy in the collision to ionize xenon atom. So it's clearly that the progress in this direction requires more and more mass. And the progress in this direction, in principle, and I already argued that the dark matter mass can be as low as a few MeV. That can be achieved by kind of being clever. Xenon one-ton also had famously some sort of excess that doesn't look that dramatic, but they have called their paper excess, and so in the electron recoil, and that's been a much of investigation and talk about these 2 points. Well, now this year there's been an update by 2 collaborations. One is LZ collaboration with Successor of Flux in the US that has set, again, they have no signal, they have set the new bounds on the nucleon dark matter scattering. And they also have released an electron signal where they also have they actually have a huge peak at this point. And that peak they have identified as the background coming from argon-30. The Xenon collaboration has countered this, saying that we don't have that peak, and then they have shown the results of the Xenon N-ton experiments, where the counting rates now are extremely small. These are in the units of 10 events per ton per year per PE. So this is by far the most sensitive counting rates that dark matter experiments have achieved. And just slightly off topic, typically these things are producing, unfortunately, upper bounds on things, but the Xenon collaboration has managed to observe one of the most rare events of radioactivity in the realm of radioactivity you can think of. So there are double beta decays, the rare events, relatively common electron capture events, what I've just observed is double electron capture, where the xenon nucleus 124 gets eats 2 electrons from the orbit, producing 2 neutrinos, and what you see the peaks from the filling of the shells, and what's they used to see it just above the background. Now it becomes a calibration line, and they even see the shape distortion due to the differentials. Yeah. So this is a fairly impressive developments. Okay. So now I'd like to get to my topic, and that's exploring how we can use this data to gain information about the 2 blind areas for direct detection. And now let me identify these 2 blind areas. First is the light dark matter, and that's what we already talked about. If we take let's say a mass of a dark matter is mega electron volt, and its velocity is 10⁻³ from the speed of light. Okay, and, if I just calculate the kinetic energy, I will get to 1 electron volt kinetic energy, and that's not enough to leave any kind of appreciable signal in xenon detector, and that's below the ionization threshold. Nothing, no sensitivity there. And that's one blind spot. And then there is another interesting to me blind spot. Suppose you have a subcomponent of dark matter that has relatively strong interaction. So you would actually think that this should be very easily seen, but in fact, no, because the particles will thermalize fairly quickly, acquire kinetic energy comparable to the kinetic energy of all the other particles inside the Earth, and that would be again well below the threshold. So these are 2 blind spots that I'd like to explore. So going back to the 2017, as I was kind of interested, or 2016, I was interested in this. To see when the people would plot the exclusion plots for the, say, scattering of dark matter on electrons, and make a point that with no limits on the left-hand side of this plot, and this along this line you can have some sort of reasonable dark matter models based on the result. Of course, once you get to the a few MeV, 1 MeV range, you typically have issues with cosmology because you have you will modify somewhat big bang nucleus. Right. So there are basically 2 approaches to address this white spot here. So one is an approach that's been exceedingly popular in the community, is to develop new techniques for detecting, for lowering the detection threshold. And for that, you can employ, say, superconductor detectors where the band gap is semiconductor detectors where the band gap is electron volt and so on. And then there's been a variety of very sort of condensed matter inspired proposals using graphenes, wild metals, DNA, and pushing the thresholds lower. And recently I've seen papers on quantum dots and so on. The problem usually is that you need many kilograms of that material to be competitive, and have the balance very good. Okay, so this is not very easy to achieve. So just to make this point again, so the xenon experiments have counting rates as 10 events per ton per year per keV, but with energies above a keV. And this attempts to measure recoils as at low energy. They using novel techniques. They run into the problems. You will see the scales here. It's 10 to the 5 events per kilogram per day. So this is like 10 order of magnitude difference between the countries, but with the sensitivity to sub-EV range. Very well. Let's just go back to this schematic plot of the dark matter energy distribution inside the galaxy. We know that there is some sort of a realized population of dark matter. There is a peak here, but I'm simplifying, roughly corresponding to 200 kilometers per second, or 0.7 from the speed of light, times 10 minus 3 from the speed of light. There is a faster fraction that nevertheless has a cutoff, because if you put particles faster than 650 kilometers per second, they will leave the gravitational field of the Milky Way and fly away. So what I'm going to do now is to exploit a very small tail that nevertheless exists there, and it has to exist if there is interaction between the normal matter particles and the dark matter. So first, I'd like to discuss the scattering of electrons. Here's the papers that I've written in collaboration with Radler, Ritz, and Anne, and that's exploring the fact that we live to a large number of very hot electrons, and those are specifically occurring in the core of the sun. So the typical cross sections that we are interested. Let's say we take this WIMP idea very seriously. We are interested in cross sections that are 10 minus 36 centimeters. Well, that's the if the annihilation rate is that, then you have a roughly corrected abundance of waves. Okay. So let's say that this is just for sake of the discussion, that this is the same cross section for scattering. Let's say if we have and let's say that the particle goes through a sun where it traverses the core of the sun. Okay. So let me calculate the probability of scattering inside the core due to that cross section. So the number densities of the electrons inside the core is 10 to the 26 centimeter cube, because we have densities very easily 100 times larger than here. The size of the core, let me say, is 10 to the 10 centimeters, which give or take. And if I multiply this by the cross section that I have taken here, well, I get the probability of a dark matter experiencing a scatter here in the core of the sun. With these numbers, it's very easy to see that this is order 1. So with the probability order 1, dark matter experiences a collision inside the core of the sun. Now the velocity of the dark matter, as we have agreed, is 10 minus 3 of the velocity from the speed of light. When it gets inside the sun, it gets like a factor of 2 larger velocity. Okay, fine. However, the solar electrons have energies of temperatures of keV. So there is a large fraction of electrons that moves with a velocity of 10% of the speed of light inside the core. So they're very almost like semi-relativistic So if let's say the two particles are matched in mass, the electrons and the dark matter particle. Therefore, the two-to-two collision will velocize there will be a large fraction of the collisions that will communicate the kinetic energy of the electrons through the dark matter. So what's happening here is that with this you have a few collisions and then the particle is ejected. Of course, the sun, and here's the penalty coming in, is looking at us. Well, we are looking at the sun with the subtending 10⁻⁵ of the solid angle on the sky. And that's the penalty. Even if the cross-section of probability of scattering is order 1, the angle we see is 10⁻⁵. And this is the typical suppression 10⁻⁶ even if I'm talking about the core. So this is the suppression in the flux that we're going to have 10⁻⁶. And but what's happening here is that on top of the dark matter distribution, galactic distribution that has an endpoint, there will be a very energetic fraction sticking out to a KV range. Yes.
So Maxim, you explained that termination point is because they can escape galaxy. But so what? I mean, they may come from distant galaxies and there may be plenty of them just coming.
Yes,
from.
there will be with the characteristic, but they're not going to be much faster, right? So you can think maybe they could reach 10⁻² from the speed of light. They like remind me the bullet cluster velocity is something the cosmologists know better, is something like 1,000 kilometers per second. So
I guess I'm asking, we have microwave background through traveling through the entire universe with the speed of light, and
right.
it's around. So why can't we have plenty of very fast
Well,
dark
excellent
matter
question.
particles?
The microwave background used to be mega electron world and whatnot in energy, and the subsequent evolution of the universe cools it down to 2.7 Kelvin, right?
Yeah, but still
With the
below.
particle, if you also had initially dark matter particles going around with the huge velocities, once it's decoupled, the subsequent expansion of the universe cools these particles down to very, very, very low values, right? Then they get reheated again when they collapse into the structures, and but then again they get what? No,
They're very light. They or you assume they're headed. What?
it actually here I'm assuming that they're kind of 100 keV and heavier, right? So they want to have a little bit warmish dark matter. That's also not excluded, but it doesn't change the point. They're all below the detection threshold. Okay. So here I'm just drawing the attention that here the gain in energy is a factor of several hundred. Okay, so which puts it directly above the threshold. So what we did, we actually simulated this process directly. So we have the routines that calculate the reflected flux.
Can I also ask the question? So here in the process of scattering, the dark matter particle can in principle also lose its energy, right? And then the dark
Correct,
matter
but it's on average much slower than the solar electrons. That's what I was arguing, that the dark matter particles moves with the velocity 10⁻³ from the speed of light, and the solar electrons can easily have 10% from the speed of light.
So if you compute this, that they get accumulated and suppose that they can annihilate, and the annihilation cross section is about the same, then the constraint you get from this is much bigger.
Well, again, annihilate, but with these masses, they're not staying inside the sun. You need them to stay inside. They will
So
be
they just
ejected.
collide.
They evaporate.
It's a few GeV.
And when they evaporate, that's the the point that they have a lot more velocity, right? So here is the new constraints we in orange, the new constraints that we were able to derive. So there are constraints from xenon 1 ton experiment. There are this new attempts with more fancy CCDs here. And these are constraints from the dark matter reflected spectrum from the sun. So the idea is now that these particles are 10⁻⁶ from the total flux, but they have energy enough to ionize xenon. They come in, they do the ionization, and that's the constraint that we have. This is for contact interaction. We have also derived the constraints on interactions mediated by nearly massless dark photon, in which case these particles have a Milli charge, you can say, and the sensitivity to Milli charge is 10⁻⁹. So there's a lot packed in this plot because we have to do some medium effects in scattering due to the nearly massless mediators.
What's the difference between the orange and the purple?
There is the two types of data from xenon 1 ton. One has a higher threshold where they have seen both sides of the signal S1 and S2. So they have initial burst of scintillation and the ionization related burst of scintillation. This has typical threshold of alpha keV. And then there is another set of data that is not having S1 stamp on only the second part. And that they have a slightly different sensitivity because here the dark as S2 has a less sensitivity, and here S2 has better sensitivity. So for massless mediators, all the collisions that due to the very slow soft recoil, they're all enhanced, and so the S2 wins for the fact that
And the xenon limits are on the electron scatter.
on electron scattering. It turns out that the xenon experiments, they were all designed for looking for the dark matter nucleus scattering. They're extremely sensitive to the electron scattering as well, just because they're extremely pure, they're self-shielded, they have fantastic sensitivity. All right. So that's the balance that we have obtained. There's a world-leading balance. So many of these proposals that want to look at MEV particles here, we see this is already at the level of 10⁻�37. So the Skipper CCD, this Sensei limits are, I don't know, 5-6 orders of magnitude less precise. So they have to improve their sensitivity by 5 or 6 orders of magnitude to start being competitive with the bounds and so on.
Sorry, what is the difference between the left and right in this type?
On the left and right, this is taking into account electrons only. And this is a dark photon style mediation where you also have protons, right? So when you reflect from the sun, right, there is also a possibility of elastic scattering on protons.
Okay, so the production you still use just electrons, but
for detection you use electrons, but for production inside the sun you have to take into account the elastic scattering on protons.
I see.
It affects things. It can affect resonance. If it's a single collision, it doesn't.
I see.
Yes.
Martin, it seems that the logic is heavily based on this number 10⁻⁻36, and where it came from. I mean,
this is indeed a magic number. And it comes in as the following. So if you have the omega of X particle over omega of dark matter is equal to 10 to minus 36 centimeters squared times C, which is 1 for me, divided by annihilation cross section times the velocity. So if you have more annihilation, you have less of dark matter. If you have less annihilation, you have overclosed your universe with dark matter. So it's this number secretly has a square root of the Newton constant. That's why there is like this 10 minus 36. Yeah, but here it just comes out. We don't introduce this 10 minus 36. It comes out as in terms of limits.
Hi, Maxim. So when you say sensors need to improve their sensitivity, the fact is they just need to include this accelerated flux, right? Then they would have.
They can have a better like accelerated flux. Right?
Yeah,
if you lose 10 to the, if you agree to lose 10 minus 6, so the accelerated flux is 10 minus 6 relative to the total flux, but then why use sensei where you can have a KV scaling for us? You absolutely will use this. So here we are trying to add new results from xenon and on with the red. All right, so the upshot is that right now this provides a leading sensitivity from 100 keV to maybe 5 or 6, 7 MeV due to the fact that we have a small component. These are dark matter particles that are on the way out of this galaxy because they will fly away, but on the way they can ionize xenon and leave accretions. So we have kind of extended this logic also with Thorsten Brinkman to some other similar ideas. Suppose there is scattering, or the dark matter is light, but it can scatter 7 photons, and the cosmic rays are photons. So the cosmic rays can bump into the dark matter particles, get it into a larger velocity, and we can then have a component of dark matter that has energies extending all the way to almost cosmic ray energies, and that is way above the thresholds of the dark matter detectors and going above certain neutrino detector thresholds, and the neutrino detectors have even lower count. Very well. So it's the same kind of idea here that this flux of dark matter times 10 minus 10, that's the standard Halo model distribution. So it's 10 orders of magnitude larger than the flux of dark matter reflected on cosmic ray. I should say that there were papers in the past looking at what this large cross sections of dark matter scattering on cosmic rays can do to cosmic rays. And that is absolutely kind of an irrelevant question, not as irrelevant because it turns out that this accelerated fraction of dark matter can scatter again in the super, clean environment, and then we can have this. So we've put limits on the various cross sections using the again. Accelerated fraction, scattering of xenon 1 ton, now on the whole nucleus, and then we can set the limits. The limit has 2 sides. If you have too large a cross section, even the accelerated dark matter has enough friction to going through Earth to reach the xenon experiment, and then there will sort of spots missing. You can also use neutrino detectors, as you can scatter on the protons, for example, and then they would be seen as again some creating ionization, for example, in words. Should say that our own Yohei has had this idea independently and worked on a similar topic.
You scooped us.
What's that?
You scooped us. You scooped.
Yeah. Really, yeah. Very well. So then of course, this topic has gained some sort of interest from the community, and you can find the experiments that are at right depth to cover all range of diabase. Is the neutrino experiment in China that is located at the depth of like a few hundred meters or 200 meters, and that's just enough overburden to cover all this spots. Okay, the last topic. So we have set the novel limits in the place where you wouldn't expect any. So it's kind of interesting why this line is flat here. Trying to recall. So if the spectrum of cosmic rays would have been 1 over energy cube, then it would be straight. I think it would be exactly straight line, and if it's 2.7, it has a little bit of a tilt. So if you have a lighter and lighter dark matter, there is more of it, but you need to push it by much more energetic cosmic ray. So when you basically move towards this direction, you have to use a more energetic part of the cosmic ray spectrum. So there's different factors almost conspire to reflect. All right, so I've covered that. I want to do very briefly the strongly interacting subdominant component of dark matter. So it thermalizes before reaching the underground lab, and the kinetic energy becomes on the order of KT, which is say 300 kelvins or 0.03 electron volts, and that is definitely below the threshold of the detectors that exist, and this is typically cannot be entire dark matter, but it's kind of limited to a small fraction. So the interesting story is to how to try to see it, and there is one, even though it's thermalizes and it's subdominant, it doesn't mean that there are few particles around us, or if they exist. It's actually, there are very many, and the reason for that is that.
So you're saying that it will hit the Earth?
That people have explored. No, I'm not saying that. There will be there is a certain limit on the dark matter hitting the Earth, like the contributing to the heat generation. There are certain limits. What in principle one can set a much more sensitive limits using what I'm going to suggest.
Global warming solved?
It's going to be a deposition in the center of the Earth. I mean, like it depends, right? I mean, there was a papers that if everything gets trapped and annihilates in the center of the Earth, that will become the heat flux comparable to the radioactivity flux from the center, or maybe even larger. So it's very. It's a topic on its own. Here, what I wanted to say is that there is such a trivial consideration of the flux conservation. So if you have a fast particles with small density coming in, right, and then I was just arguing that there is a quick thermalization, then the velocities drop very dramatically, but the flux is conserved. So therefore the number of these particles grows, right? Now, if these particles are massive, they start sinking, they quickly thermalize, but then they experience random motion left and right, up and down, but it's a biased Brownian motion affected by the gravity, and so they sink, right? But the number densities grow, and they say if I have 100 GeV particle with a large cross sections, the enhancement in density can be 6 orders of magnitude very, very easily. So we call this effect as traffic jam, because there's like you velocize and you come to almost a complete stop. And then if there is fewer GeV in mass or lighter, there is also a flux of particles who have come back from the center. So in principle, this is all well understood by now, and it's all calculable. And the enhancement for the 1 to 2 GeV mass particles can be as large as 14 orders of magnitude. So there is a theorist at New York University, Glennis Farrar, who advocates some exotic particles that she calls sextaquarks, right?
Sexaquarks.
Sexaquarks.
Sexaquarks. She'll be here in the spring.
Very well. That what these particles have a non-zero baryon number, they cannot annihilate themselves. So what I'm trying to say is that their abundance will be 14 orders of magnitude larger than the abundance elsewhere. This 14 orders of magnitude has Earth's lifetime when you build it, because you accumulate throughout the Earth's so even though these particles may be like 10⁻⁶ from the overall abundance of dark matter, there will be an additional huge enhancement here due to them trying to redistribute themselves over the volume of the Earth. Now, we had an idea where can we sort of accelerate the dark matter. So we will try to reproduce the same ideas that I just had before, like collision with energetic particles, and trying to use the dark matter detectors that are very sensitive to even single collisions to have this working in one scheme. The thing about the some of the labs, underground labs, they have nuclear accelerators. So in particular, Keith gave a talk here last month using some of the results of the Luna accelerator in Gran Sasso that is operating at 400 keV, and now there is a new machine at 3 MeV going into the Gran Sasso lab. So there is a large flux nuclear accelerators. They're all done for the sake of studying nuclear reactions in a sort of clean environment. But one can imagine that if there is a large enhancement of the number density of particles, one can actually just have the dark matter detector shielded nearby, and then the collisions of the protons with this dark matter targets will create a velocitized dark matter. So we have estimated or calculated the fluxes of various particles for the set the energies of 400 keV or the 1 MeV, and there's a large fraction of dark matter particles that have velocity, large velocities, you can much above the thresholds for detection. So if one implements this scheme, one could cover a lot of additional parameter space. Here I'm playing with the parameter FTPI, and that is the fraction of dark matter inside these exotic particles. And using this scheme and the already available Luna accelerator and the accelerator in China called Juna, not to be confused with Juno experiment. So one can cover quite a bit of the parameter space, otherwise completely unattainable and yeah. So right, so I think I'd like to finish at this point. I have argued a very simple thing that if you have a relatively sizable cross section, then exploring double collisions between dark matter first with some energetic particles, would it be the solar electrons or cosmic rays or even the beam particles that we have in the underground laboratories, and coupling it with the dark matter detectors and the neutrino detectors. All that scheme provides an additional sensitivity to dark matter particles that is capable of covering a lot more of the parameter space for these models. And, many of the dedicated experiments try to lower the thresholds for detection will have to be improved by, say, 5-6 orders of magnitude to start being competitive, in particular with this idea of the solar reflected dark matter.
Maybe you can have a few questions. More? Yeah, please go ahead.
Yeah, so going back to the scattering inside the sun. So if you have this dark matter particles, which can get large velocity from scattering in stars, right? And some of them can get velocity large enough to escape the galaxy. So, and this is not an equilibrium process, right? So the dark matter halo gets heated and it operates slowly. Is it correct?
The amount of yes, these particles leave, but the overall fraction of dark matter that's recycled that way is very small.
Okay, so the time scale at which this happens is
Yeah,
very
it's
large.
very small. It's very small.
More questions? Yeah, please.
I have like a general question. I've been a spectator on this field for like 25 years. And it used to be that it was all about WIMPs, right? The high mass had to be high mass. What do we really know about dark matter? What do we fundamentally? We know it's cold. Right?
Well, this is the main premise of the talk, right? So if we have invested so much money into looking for one thing, even if it's fully more, perfectly motivated, we'd like to explore on the sides, right? Because what if it's not a WIMP of 100 GeV mass, right? If it's
I'm not questioning that. I'm just asking, what do we really know about the dark matter?
we don't know much, and that is because the dark matter. Well, we know that it's cold or maybe warmish, right?
We know most of it's cold, right?
Right. Most of it is cold. Now gravity has this feature that it can be, particle action like 10⁻⁶ electron volts, but particles that were sitting still, right, in the universe, roughly speaking. Or it can be a TV WIMP, or it could be a small black hole. And these things, from the point of view of how they form structure, they're roughly the same, right? So there can be some questions, we had a talk a couple of weeks ago by Oren, who was trying to argue that, or some papers he referred to were arguing that, oh, maybe there is some evidence for self-interacting dark matter, right? At this point, I don't think it's strong enough evidence. If it's but if let's say if it would be confirmed that it's self-interacting dark matter, then I guess black holes would be out of the picture because they cannot be, but they can still contribute at the level of 10% or a few percent, right? We cannot rule out that.
Maxim, so about last part. So when you talk about using those accelerators to kick those dark matter, what's the intensity of those accelerators and what do people build that for?
Well, they're built for looking for nuclear reactions that occur very rarely, because so when what happens is that and also they build for measuring these reactions exactly at gamma peak energies, where the rates are already Coulomb suppressed, right? So if you go and try to measure certain reactions, I don't know, carbon 12 plus alpha, some at gamma peak energies here on Earth, you get so few of these photons that you would be swamped by the background. So that therefore the idea is to go underground, where the gamma backgrounds are 5-6 orders of magnitude less, right? And so you suddenly gain visibility. And so the cross sections that Keith has shown for deuterium plus proton to helium-3 plus a gamma, that is very crucial for the BBM, is measured at Grand Sasso lab using 400 keV.
I guess the question is about the luminosity. You know, how many
the luminosity, the currents are at sort of 1 milliamp range. So these are fairly from the party. So that because the energy is not that huge, the power is not that huge, right? As we know very well, it's the accelerator power that is the main. Like if it would be 1 milliamp at 1 TeV, that would be an awesome accelerator, right? But no, it's 1 milliamp at a few eV energy.
The associated question is, of course, the diagram you accelerate the dark matter can also be parity producing dark matter at the collisions. So
we're looking here at a few GeV. Yes. So
for those strong interacting ones, kick the flux better, or there's a balance point.
There are strays from colliders, from the LHC and so on, right? But if you have a light mediators and light dark matter, it's very well known that the collider constraints are also weakened because everything goes more or less forward.
All right, so let's thank Maxim again. Next week, we have the last talk from out of town. Very good. Very nice. Just curiosity.